This video is going to be broken up into two parts. The first part of this video, we're going to talk about complex conjugates. So you'll remember in an earlier video, I mentioned the notation for complex numbers. Well, I want to make it a little bit more well-defined now. So the kind of arbitrary complex number is denoted with the letter Z. You'll notice I always cross my Z's, and this is simply so that neither I nor you ever confuse them with a 2. Okay? So again, Z is the arbitrary complex number A plus BI. So the next thing I want to do is I want to give you the definition. The complex conjugate of the complex number Z is denoted Z bar, so that's Z with a bar on top of it, and Z bar is equal to A minus BI. So Z and Z bar have the same real part, but opposite imaginary parts. So let's talk a little bit about some properties of Z and Z bar. So the first thing is, if you add them together, you always get a real number. So you can see here, what I'm saying here is you're adding A plus BI and A minus BI. And since the imaginary parts are opposites, they just cancel out. So sure enough, the sum of a number and its complex conjugate is always real. The difference between a number and its complex conjugate, on the other hand, is going to always be imaginary. So if we subtract A minus BI from A plus BI, you can see here that the real parts, because they're the same, are just going to cancel out. And when I subtract negative BI from BI, since subtracting a negative turns it positive, this becomes 2BI. So the difference between a number and its complex conjugate is always purely imaginary. But here is the part that's perhaps the most interesting, and that is if we multiply a number by its complex conjugate, the product of Z and Z bar. So let's multiply A plus BI by A minus BI. So remember, in the previous video where we talked about multiplying complex numbers, we were mentioning the fact that the good news is that the distributive property carries over from when we were talking about purely real numbers. So basically everybody gets multiplied by everybody else. So here we go. We'll have A squared minus ABI plus ABI minus B squared I squared. So again, feel free to pause here and work it out for yourself to make sure you understand, but the basic idea is that we're multiplying through here like so. So everybody gets multiplied by everybody else. Now look what happens. I have minus ABI and plus ABI. So those two are just going to cancel out. And then here I have negative B squared I squared. And as you remember, I squared is -1. So negative B squared I squared is just going to be plus B squared. So in fact, the product of a number and its complex conjugate is just the sum of the squares of the real and the imaginary part. So let's do a real small example here. So this would be another great place for you to pause the video and see if you're with me. So if I take the complex number 2 minus 7i, what is the complex conjugate of that number? Pause the video, answer me, see if you got it right. Good. The complex conjugate is 2 plus 7i. So I'm actually going to label here for your information. Here our complex number z is 2 minus 7i, and the complex conjugate z bar is 2 plus 7i. So if I multiply these together, I'm not going to go through all of the motions on paper, but remember, when I multiply, everybody gets multiplied through. So the 2 gets multiplied by the 2 and the plus 7i, and the minus 7i gets multiplied by the 2 and the plus 7i. So it's going to look very, very similar to what we had up above, except of course with actual numbers. So what are a and b here? A is 2, b is 7. It's positive 7 for z bar, and it's negative 7 for z, but that doesn't matter so much when it comes to talking about their squares. So the sum of the squares of a and b is 2 squared, which is 4, plus 7 squared, which is 49, so that is 53. So in some sense, this is the really big thing that we're going to use a lot when we're talking about complex conjugates. That the product of z and z bar is always real, and it's always the sum of the squares of the real and the imaginary parts. So I'm going to go on to the second part of the video here, where we're going to talk about division of complex numbers. But complex conjugates are going to be on the backs of our minds, and we're going to use them in that piece. So we're going to talk about dividing complex numbers. And in a sense, what I'm going to say here to guide us is, just like multiplying any two complex numbers, you got a complex number back. So it could be written in the form a plus bi. I'm going to say here, for any two complex numbers, let's call them z1 and z2. The quotient z1 divided by z2 can be written in the form a plus bi. So what I'm saying to you here is, it is possible to take any two complex numbers and divide them and not end up with any i's in the denominator. So we're going to do a few examples, and we're going to start with 1 over I. This is a nice, clean example. And what I'm going to point out here is, yes, I have an I in the denominator, but as you all remember from our previous lesson on multiplying complex numbers, I squared is -1. So if I could just take that I in the denominator and multiply it by I, well, then I have I squared in the denominator, which is -1, and we're really comfortable with dividing things by -1. So I'm going to go ahead and do that. And of course, what you all also know is that you can't just go around multiplying the denominator by I. If you're going to multiply the denominator by I, you also have to multiply the numerator by I, so that in the end, you've multiplied by 1 and you haven't actually changed the value of your expression. You've only changed kind of the appearance of it. Well, what do we get here? On top, we have 1 times I, which is I. On the bottom, we have I squared. And as we know, I squared is -1. And we all know that dividing by -1 is the same thing as multiplying by -1. So it turns out that 1 over I is actually the same as -I. For those of you who like playing around with properties of exponents a little bit, you could actually take this example and see if you can tie it in with what we were saying in the previous example about powers of I always moving in cycles of 4, and realize that what we just showed here is that extends to negative powers of I as much as it extends to positive ones. But I'll leave that for you to think about. Come talk to me in office hours if you'd like. Let's try another example. So this is going to be where complex conjugates come up again, right? So let's say that I have something like 3 over 2 plus I, okay? So again, my first complex number, Z1, is purely real. That's just so that it's a little bit simpler. I will definitely do an example next where neither one of them is purely real. Now, here's the thing. I have an I in the denominator, but multiplying top and bottom by I isn't going to help me because of the distributive property. If I multiply, so just bear with me here, if I multiply top and bottom by I, well, that doesn't do me any good. I have to distribute that I through. And yeah, I times I is I squared, that's nice, but I times 2 is 2I. So I'm still going to be left with i's in the denominator. So multiplying top and bottom by I doesn't achieve what I want, namely, it doesn't achieve the removal of i's from the denominator. So we're sitting here thinking about it, and then we're like, wait a minute. If I multiply any complex number by its conjugate, I get a real number. That's the sum of the squares of the real and the imaginary part. So if I multiply 2 plus I by its complex conjugate, I'll get a real number back. What's the complex conjugate of 2 plus I? Pause the video and answer me. You're right. The complex conjugate of 2 plus I is 2 minus I. So just like we did in the previous example where we said you can't just go around multiplying the denominator by things. If you multiply the denominator by something, you also have to multiply the numerator. We're going to go ahead and multiply the numerator by 2 minus I as well, so that in the end you are multiplying by 1. And I hope by now this is already clear, but just to reiterate, the distributive property never sleeps, so I'm going to have to distribute in the numerator. In the denominator, if you'd like to go through the whole process of distributing, you can, but you already know that it's going to be the sum of the squares of the real and the imaginary part, so you could just use that. So we have 6 minus 3i, and then on the bottom, the real parts are 2, so 2 squared is 4. And the imaginary part is either 1 or -1, depending on which one you're looking at. Either way, the square is 1. So I have 6 minus 3i over 5. Now, I set up here, for any two complex numbers, z1 and z2, the quotient can be written in the form a plus bi. So how do I take this, 6 minus 3i over 5, and write it in that format? Well, remember, when you're just dividing by 5, you can multiply each piece of the numerator by 5. And so you'll have 6/5 minus 3/5 I. Okay, so the real part here is 6/5. The imaginary part is -3/5. Let's finish this off with an example where neither the numerator nor the denominator are purely anything. They're both complex. So say I have 2i plus 5 on top, and 3 minus 4i on the bottom, okay? So same thing. I want to end up with just a regular complex number where I can write it in the form a plus bi, and I can answer the question, what's the real part, what's the imaginary part? And in particular, that entails making it so there are no imaginary numbers in the denominator. Well, just like in the previous example, we can see 3 minus 4i, it's not going to do me one bit of good to multiply that through by I. But the complex conjugate is here to save the day. What is the complex conjugate of 3 minus 4i? Pause the video. You're right. The complex conjugate of 3 minus 4i is 3 plus 4i. And again, just like before, you can't go around multiplying the denominator by 3 plus 4i. If you multiply the denominator by 3 plus 4i, you also have to multiply the numerator by 3 plus 4i, so that in the end, you have multiplied by 1. Big distributive property situation, right? So this is really an example where we're combining the skills from our previous lesson with the skills from this one. I encourage you to pause the video here, go through the process of distributing up on top, and then restart the video and see how you did. Okay, let's do this. So when we distribute, the distributive property never sleeps. So on top we'll have 15 plus 20i plus 6i plus 8i squared. We'll clean that up in a second. Now on the bottom you could also distribute, but remember, the product of a complex number and its complex conjugate is always the sum of the squares of the real and the imaginary part. That's going to save you a ton of time if you just kind of learn that. And you can learn it again by kind of looking over here and watching back over that part of the video. The real parts are 3, so 3 squared is going to be 9. The imaginary part is 4 or negative 4, depending on which one you're looking at. Either way, the square is going to be 16. So I have 25 on the bottom. Now look at the top. So I have 20i and 6i. So those are going to combine into 26i squared. And then I also have plus 8. Oops, I'm sorry, I misspoke. 20i and 6i are getting combined into 26i. And then 8i squared, because I squared is negative 1. I squared times 8 is going to be negative 8. So the 15 plus 8i squared combines to 7. The 20i and the 6i combine to 26i. So I have 7 plus 26i over 25. And again, if you're keeping up with what I said at the beginning, the quotient of any two complex numbers can be written in the form a plus bi. So this can be written in the form 7/25 plus 6/25 I. So you took two complex numbers. One had a real part of 5 and an imaginary part of 2. The other had a real part of 3 and an imaginary part of negative 4. And the quotient was 7/25 plus 6/25 I. This concludes our conversation about dividing complex numbers. In the next lesson, what we're going to do is we're going to take this conversation and we're going to tie it back to our conversation about polynomials.